Let me start. I am János Szebeni. I am pleased to open this afternoon session on safety and toxicity of nanomedicines. Needless to say that safety and the lack of toxicity is as essential in our field as efficacy. So it is very important to thoroughly study this field. However, toxicity is a very broad field. It's impossible to cover all nanotoxicities in a session, so we focused on immune toxicity, the interaction of nanoparticles, nanomedicines with the immune system. However, the immune system is very broad, so we had to focus further our attention, our discussion here on the interaction of nanomedicines with the innate immune system. So we will hear about complement, antibodies, macrophages, other immune cells, which are highlighting the interactions and potential toxicities. We have the fortune of having here the best experts in this particular very focused field. So you will have a very broad, within the focus, highlight of every possible interaction. And starting this line, I am going to talk about a phenomenon which we refer to as infusion reactions, and very broadly about the roadmap and strategy to overcoming infusion reactions to nanomedicines, which is an important issue among others. By way of background, let me remind you that infusion reactions are complex immune-mediated side effects that occur at a therapeutic dose of intravenously administered pharmaceutical products in a small fraction of patients. And here are the two important parts of this sentence: that therapeutic dose, in other words, those which usually or in most cases should not cause any problem, and in a small fraction of patients, that is to say, not everybody, but only a small fraction, the 1 to less than 10% actually indicates, or more precise, if you say 1 to 2%, but in some medicines it can be as high as 40%. So this is a very inaccurate estimation. These products are diverse and include both traditional and like biologics and small molecules, and novel nanotechnology-based pharmaceuticals. So the phenomenon of infusion reaction is much broader than as if it were occurring only in the nanomedicine field. And although infusion reactions are not unique to nanomedicines, they represent a significant hurdle for the translation of nanotechnology-based drugs products, and I will focus on these issues, why. So the goal of my presentation is to give a very broad analysis of and presentation of symptoms, drugs, and clinical relevance of infusion reactions, the progress of its understanding, old and present theories, assays, strategy for prediction, and a roadmap, a plan, an idea how to control it better, highlighting the gaps, and a holistic approach. These will be probably the most general statements what I will give. Many other details will be presented by the other lecturers today. Well, symptoms and drugs, just shortly: hypertension, flushing, rash, respiratory distress, difficulty of breathing, which develops shortly after administering the drugs, chest pain, back pain, edema, anxiety, fever, laryngospasm, suffocation, myocardial infarction, shock, and death. Unfortunately, death can also be the consequence of these reactions. Fortunately, very rarely, but it still occurs, and when it occurs, it's a red flag for continuation of the drug, at least in a few cases. Now, the drugs and drug categories which cause such reactions include liposomes, micellar drugs, monoclonal antibodies, PEGylated nanoparticles, radio contrast media, and The significance of the phenomenon lies in these facts. Well, the clinical significance depends on the risk versus benefit ratio. For example, in cancer, systemic fungal infections, when the drug is absolutely essential for survival, the significance of these reactions are minor. The risk-benefit ratio is very much towards the benefit. However, there are indications, nanomedicine indications, where such side effects just cannot be afforded. For example, the cardiovascular applications. In case of large phospholipid doses are required, or the time the administration is limited because of the efficacy window. And in this case, the absence of immune reactions is absolutely critical. In the case of cardiovascular application, this is because the most dangerous side effect is MI and cardiac distress, which can be lethal. Actually, all the patients who died in infusion reactions have a cardiac problem. Now, for the pharma industry, these reactions are increasingly important because of the fatalities, because these reactions cannot be predicted by standard allergy tests. They may lead to drug withdrawal, as I will show some cases, and the regulatory authorities increasingly demand experimental verification of short and long-term tolerance for side effects. This table illustrates the severity of the problems for a certain drug category, namely PEGylated nanopharmaceuticals. These are the products which came out relatively recently, within a couple of years, and in this list, 4 have been withdrawn from the market. Most recently, this drug which I show here as the final. Some more details into this, a very interesting story, in that it was a sensation. This company developed a new drug, a PEGylated aptamer against thrombosis, and they invested a lot. There was a lot of excitement about this introduction, but what happened was that after a few reactions, the clinical trials had to be stopped. The company had to withdraw the drug. They almost broke in this problem, although not more, only you can see here 3 out of 640 patients developed reactions. It's a very small fraction, 0.5%. So this is even such a few cases is enough to send a drug to the basket. Now, obviously, a lot could be told about these reactions, why they happened. Over time, there have been a lot of efforts to understand why these reactions occur. And it goes back to the 1960s that Coombs and Gell set up their categorization of adverse immune reactions. And these immediate allergic infusion reactions clearly belong to the type 1 allergy category because of the time course. However, the mechanism, originally it was defined as IgE mediated. In case of infusion reactions, in most of the cases, it is not IgE mediated. It is IgM and IgG mediated, as you see later. Now, in the 1980s, Tony Hughley in California, who discovered the anaphylatoxins, very early described that these reactions are due to anaphylatoxin release. And anaphylatoxins are produced by complement activation. So the complement activation theory was already there in the 1980s. And in the 1990s, another mediator came to the picture, bradykinin, particularly in the contrast and dialysis reactions as their mechanism. And then in the 2000s, partly because of our coming to this field, we reinforced the Hughley theory that complement activation is playing a causal role in these reactions. We came up with this term, CARPA, complement activation related pseudoallergy, which term combines the mechanism and also the fact that it is not IgE mediated. The word pseudoallergy refers to this fact. And and later, last year and this year, another theory surfaced which highlights that another mechanism, direct stimulation of allergy-mediating cells. Now, the problem with this theory that although it is true, direct interaction with certain cells represent a cause of the reactions, but this theory excluded complement as a mechanism, as that created some this dispute in the literature, which will be discussed later in more detail. So now I have to speed up because the time is running out. This debate is now discussed in papers. You can grab a few flyers and reprints. The fact is that the complement hypothesis has a lot of evidence over 30 years. There's no doubt that complement is playing a role. The only question is whether in cases when there is direct stimulation of immune cells, whether complement is a contributing factor or not. So this is presently a debate in the literature and among us. Taken all together, there is a very complex mechanism of CARPA, or complement activation-related pseudoallergy, where the nanomedicines activate complement, the complements activate certain cells, including mast cells, basophils, secretory macrophages, white blood cells, platelets. All these lead to a release reaction of a dozen of allergy mediators, which act on effector cells, smooth muscle cells, endothelial cells, and that leads to the symptoms listed here. This is the physiological background of the symptoms which I originally mentioned. There is another important important aspect of this new theory is the double hit, that the complement activation actually promotes the effect or accelerates the effect of direct contact of nanoparticles with certain cells, the secretory allergy-mediating cells. So there must be most likely at least 2 hits in order to reactions develop, and that explains why only in a few people we see the reaction, because although in most one or the other hit may be present, but the 2 together might not be present at the same time. There are CARPA tests. I wouldn't go into details in this, just highlight our PEG test. Dr. Urbanic, the last speaker, will go into details around it, and also Dr. Deji in another context. We have just one sentence that we have a strategy to diagnose and predict complement-mediated reactions, which include in vitro testing, in vivo testing, depending on the outcome of one or the other. And we believe that the combination of the 2 gives the best estimation or prediction of the potential toxicity. There is a roadmap, a strategy for better control. In particular, in order to get a handle of these reactions, we need to identify which are the best mediators, or which are the really important mediators, and there are a lot. Nominees, including all these. At the moment, we do not really know which are the most important. For example, in pigs, we know that thromboxane A2 is the immediate mediator of the reaction, which can be triggered by complement. But we do not know anything about serotonin, leukotrienes, a little, not very conclusive, and all the others. So there's a lot of work ahead of us to unveil which are the contributing mechanisms. And the model, we promote the pig model, but we also know that the reaction can be observed in rats, mice, dogs, although each model has its pros and cons. At the moment, we vote for the pig. And obviously, the more we find out about the mechanism, the better control we can expect to override the mechanism. Here are my conclusions. Infusion reactions remain an unsolved problem for many therapeutic and diagnostic medicines. The current experimentally derived evidence is more in favor of a role of complement activation in infusion reactions than its irrelevance. The porcine immune toxicity model is uniquely applicable for practical evaluation and risk assessment. The model, complemented with in vitro assays, enables the prediction of CARPA and elaboration of safe administration protocols. Let me acknowledge my colleagues, who most of them are here today, so I didn't list their names, and just mentioning that all what I have told are now in press in one of the next issues of Nature Nanomedicine. Okay, so this was my presentation, and I maybe just if there is any question, I would address. Yes?
I must admit I have large problems in understanding why you use this pig model. Okay. It has been well known for more than 30 years that pig contains intravascular macrophages in the lungs, so-called pulmonary intravascular macrophages. I was myself involved in a study with particles 5 years ago that was completely safe in humans. We had injected it into more than 100 persons at the time when a researcher asked for receiving this product, injecting it into a pig and managed to kill the pig due to hemodynamic effects. And I don't understand why to test nanoparticles in such a model where you have such dramatic effect of all nanoparticles injected into pigs.
Thank you very much for the question. This is the most critical question in our field, which has been asked ever since we developed the porcine model and proposed it. The very simple answer is that the exaggerated or extreme sensitivity makes it a good toxicity model. The reaction in the pig is not reflecting what is happening in a normal human individual. It shows exactly, or not exactly, but at least part of the symptoms overlap with the symptoms of hypersensitivity reactions. People who die in a reaction display the same cardiovascular collapse and stress what we see in the pig. So the pig is a model for one particular question, whether in a small fraction of people, it is a disease model, a disease of the hypersensitive people, whether that can occur in any situation. I agree with you. If somebody wants to make a claim about the safety and they see the reaction only in pigs, that drug is still okay. But it draws attention to the possibility that in a certain small fraction of individuals who act like pigs, this reaction can happen. And for that reason, it is a very good model to study the mechanism, because we believe that whatever happened in those people who die, we see the same in the pig.
I think it's much more a danger that people stop development of very promising agents.
We never say that seeing a reaction should stop development. What we say is that, okay, there is an alert. Please pay attention to this possibility that you bring the drug to market, and in 3 years, 3 deaths occurs, and then you have to go back to the bench to see why. And this has happened with many drugs. This is why it was very important to find a sensitive model. All the other models are not sensitive, simply not sensitive. Pig, you don't see the reaction in rat, in mice. You see the reaction in dogs, but not in every dog. You don't see the reaction in rabbits. So we had to find, and in toxicity, in toxicology, we always find the most sensitive model. Okay? Okay, then if any more questions?